Here's our video for scientific notation, otherwise known as SciNot. Before we really get into what scientific notation is and how it's used and how we work with it, we need to talk about something called the dead baby rule. We explained in class why this is called the dead baby rule, but just for intents and purposes, know that whenever we refer to the dead baby rule, or remember your dead babies, we're talking about the fact that it is a scientific practice to write the 0 in front of a decimal point. In other words, you have to have this 0 right here in front of your decimal point, basically so that you know that there is in fact a decimal point there. Like I said, we explained why we call it the dead baby rule in class, but if you want to know in more detail because you weren't here or something, come ask your teacher. Okay, on to the actual scientific notation stuff. So, scientists must frequently deal with numbers that are either very, very large, like that huge number you see. That's actually, this number right here is actually a really important number in chemistry. We'll talk about it later. It's something called Avogadro's number. So we frequently deal with numbers that are very, very big or very, 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 very small. I mean, you see all those zeros there. That's a very, very small numbers. So if you had to use those numbers a lot, it would just take forever to count all those zeros, to write all those zeros. Scientists tend to get very lazy after a little while. So we created a method where we can convey the information that these very big or very small numbers have, but convey it very, very quickly. We started writing shortcuts for these very, very long numbers. So the system that was created comes with two parts. It has a coefficient part and it has an exponent portion. The coefficient is some number between 1 and 9.99999, endlessly repeating, and the exponent represents how many times that coefficient is multiplied or divided by 10. That exponent could be positive, that exponent could be negative. Essentially, that just represents whether you're multiplying or dividing by 10. If it's positive, what that tells us is that our coefficient is actually multiplied by 10 however many times our exponent tells us. So 10 to the second power, you multiply your coefficient by 10 twice. In other words, you're multiplying really by 100. 10 to the 4, you're multiplying by 10 4 times. We use positive exponents when we're trying to represent big numbers. If it's a negative exponent, that's what we typically use for small numbers, because that's really, you're just saying how many times you're dividing by 10. So 10 to the negative 1 means you're dividing by 10 one time. 10 to the negative 3, you're dividing by 10 3 times. Okay, so here we have an example of when we need to take something standard and turn it into scientific notation. Right now we have 32,400,000,000, essentially a number with 8 zeros on the end. If you had to write this number 5, 6, 7, 8 times, you're going to get really annoyed because that's a lot of zeros to keep writing over and over and over. So we're going to take it and turn it into scientific notation just because it's going to be easier to deal with. So first question you have to ask is, well, where's the decimal? Looking at that number, there's no decimal there. We didn't give you a number that has a decimal already there. If we don't give you a number with a decimal, you are allowed to assume that there's an imaginary decimal sitting at the very, very end of your number. Okay? It's not actually there, but you have to pretend that it's there. Next question you ask, well, where does it need to be if I'm going to have a number between 1 and 10? Well, the only place that you can put a decimal and turn this number from a very, very big number and instead have a coefficient between 1 and 10, really 1 and 9.99999, would be to put it right there between the 3 and the 2, turning your 32 billion into 3.24. So, last thing you have to do, you have to figure out, well, I have where the decimal is now at the end. I know where it needs to be, so let's count how many places we would have to move it. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I would have to move the decimal 10 places to get it from where it is to where it needs to be. That tells us what our exponent is going to be. We're going to turn our 32,400,000,000 into 3.24, our coefficient, times 10, and we moved our decimal 10 times. Last thing you have to figure out is, well, does that need to be positive 10 or negative 10? There's two ways you can kind of remember it. If you move your decimal to the left, like we did here, then you're going to have a positive exponent. That's one way of remembering it. Just remember, if you move the decimal left, it's going to be positive. The other way you can go about it is, well, I took a big number, 32,400,000,000, I turned it into a smaller number, 3.24. If you take a big number and make it smaller, you need to have a positive exponent to show that while my coefficient is 3.24, that really represents a number that's much bigger than that. So if you move the decimal to the left, it's positive, or if you take a big number and make it small, that's going to be a positive exponent. Here's another example, 0.0000000567. Same set of process, same three questions. First off, where's the decimal? Well, you don't get to assume it this time around because we give you a number with a decimal. It's right there. So there's the decimal. Well, where would it need to be? Well, if I'm going to have a number between 1 and 9.99999, it would need to be right there between the 5 and the 6, turning my number from this really, really small decimal into 5.67. Lastly, same thing we did with the big number. We're going to count how many times I would have to move it from where it is now to where it needs to be. 1, 2, 3, 4, 5, 6, 7, 8. Which means here's my coefficient, 5.67 times 10. And we moved it 8 times. But then notice this time we moved it to the right. Well, just like there's kind of a way to remember whether it needs to be positive, there's another way to remember whether it needs to be negative. If you move your decimal to the right to make it into scientific notation, that tells me it's going to be negative. So I moved it 8 times, but since I moved it to the right, that's going to be negative 8. The other way you can kind of go about thinking about this, if you take a small number and you make it bigger, which we did, we took something that's, to the millionths, and turned it into 5.67, I took a very, very small number and I made it bigger, which means the number that I write has to actually technically be a really, really small number. So if you move your decimal to the right, it's negative, or if you take a small number and make it bigger, like we did here, then that also has to be negative. Here's a few more examples if you want to take some time and work on them on your own. We'll talk through a couple of them here, and I'll just write the answers for a bunch of the other ones. Starting with that first one, 17, we have the imaginary decimal at the end. If I can get it in there. It needs to be between the 1 and the 7 to turn my 17 into 1.7. So I'm going to move it one place over, which turns my number into 1.7 times 10 to the 1. Since I moved it one time, get an X in there. But since I moved it to the left, it's going to be positive. Or because I took a bigger number and made it smaller, 17 to 1.7, that also tells me it needs to be positive. Let's look down at that big one at the bottom, 7,631,000. Well, there's no decimal in that number, so I'm going to put it there. And I'm going to start moving it to where it needs to be. Well, if I'm going to have a number between 1 and 9.999, I got to have it there to turn that 7 million into 7 point something. So I'm going to start moving it. 1, 2, 3, 4, 5, 6. I moved that decimal 6 times, which turns my 7,631,000 into 7.000631 times 10 to the sixth power. And since I moved it to the left, that's going to be a positive 6. Or because I made a bigger number smaller, that's going to be a positive 6. Let's look at a couple of on the other side. Let's look at that 0.00370004. So I have my decimal there. If I'm going to create a number between 1 and 9.999, I'm going to have to move it between the 3 and the 7. So 1, 2, 3. So I get 3.7004. And again, we'll talk about why we can drop those extra zeros a little bit later. Times 10. We moved it 1, 2, 3 times. But since we moved it to the right, that's going to be a -3. Or because we made a smaller number bigger, we turned our 0.00370004 into 3.7, effectively. That's going to need to be a negative exponent. Let's look at the one right below that, 0.00000038. We have the decimal there, right between those first two zeros. And we're going to need to move it 1, 2, 3, 4, 5, 6, 7 to create 3.8 times 10, let's close out my 8 there, times 10 to the 7. But since I moved it to the right, that actually needs to be a -7. So here, if you want to pause the video here and complete those other 4 examples, you can check it with us. Or here are the completed answers so that you can now check for yourself. So everything that we've been doing up to this point, we've been converting standard notation into scientific notation. But you're going to have to be able to go both ways, both standard into scientific, but you're also going to have to go scientific back into standard. So effectively, we're going to be doing the same thing that we were doing. We're just going to be doing it backwards. Remember that if a number is ending with a positive exponent, that means you're multiplying that number by 10 as many times as the exponent says. So what you're going to end up doing is you're going to move the decimal point to the right. You're going to do the opposite of kind of how you went into it. You're undoing the scientific notation. So since a positive exponent meant you originally moved the number to the left, when you undo it, you're going to move it back to the right. Same way with a negative exponent. You're technically dividing by 10. So you're going to be moving the decimal point to the left, the opposite of what you did to get into the scientific notation in the first place. So we have a few examples here of doing that, similarly to how we did the last set of examples. I'll do a few. You can pause the video, and then the rest of the answers will pop up. So let's look at that first one. 2.926847212 times 10 to the positive 9. I know it's a little hard to see here, but your notes has it pretty clear. So times 10 to the positive 9 means we're going to take that number, we're going to multiply it by 10 9 times. Well, you could do that on your calculator, times 10, enter, times 10, enter, times 10, do that 9 times. Or if you know the shortcut, multiplying by 10 means you're just moving your decimal to the right every single time you'll multiply by 10. So since I'm multiplying by 10 9 times, I'm going to move my decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9 times, which means my 2.926847212 times 10 to the 9 turns into 2.6847212. Go in and complete some numbers there. In other words, it just moves that decimal all the way to the end. You can choose to write it or not write it. Well, again, we'll talk about the rules of when you do or don't write that here in a little while. Let's look at that last one. 5.92 times 10 to the negative 2. Times 10 to the negative 2 means we're going to move the decimal twice, and we're going to multiply by 10 twice. So we're going to move it to the right 1, 2 times, which means my 5.92000 turns into 592.000. I moved my decimal 1, 2 times. If you're dealing with negative exponent, remember, negative exponent means you're really dividing by 10. I know it says times 10, but a negative exponent means when you actually do the math, you're actually dividing by 10. So let's look at the third one down for just a second. 8.429 times 10 to the negative 1 times 10 to the 1 means you're moving it 1 time. The negative tells me since I'm dividing by 10, I'm going to move the decimal once to the left. So I'm going to take my 8.429, and I'm going to move my decimal one place over, which means my 8.429 turns into 0.8429. We add that 0 before the decimal for the dead baby rule as we described at the beginning of the video, so that we know and can very clearly see that there's a decimal, supposed to be a decimal there. Let's look at the one right above it this time, though. 4.92 times 10 to the negative 5. So, times 10 to the 5, we're going to be moving our decimal 5 places. The negative tells me I'm dividing by 10. In other words, I need to move my decimal to the left. So, let's start moving it to the left. Well, there's the first place, but I run out of spaces. There's nowhere else for me to move it. So how we solve that problem is, well, we just kind of pretend that there's an infinite number of numbers behind it. There's another one, there's another one, there's another one. So we've moved it 1, 2, 3, 4, 5. That's where it needs to be. But we got to put something in all those little bumps, all those little gaps. And the only number that you can ever add that doesn't really change anything about the number itself is 0. So you're going to add a 0 to every one of those little gaps, everywhere that didn't have a number, just like that. So when we take our 5.92 and we times 10 to the negative 5 and we turn that into a standard notation number, we end up with 0 point, because again, dead babies, 0, 0, 0, 0, 4, 9, 2. We use those extra zeros to fill in those missing gaps so that our number can essentially be put in the position where it needs to be. Here's where you would pause the video. I'll go ahead and fill in the rest of the answers. Try them yourself, and you can check against what's about to pop up on the screen. Here are the rest of the answers for those two in the middle on the left and the top and the bottom over on the right. Like I said, check your answers, make sure they match. You filled in as many zeros as you need to, especially with the second one on the left and the top and bottom ones on the right, because you got to make sure that you have enough zeros so that all of your other important numbers are sitting in the right place values where they're supposed to be. Here's a couple more examples of just some incorrect scientific notation that we couldn't choose to fix. That first one says 524 times 10 to the 3. Well, 524 is not a number between 1 and 9.99999, so we have a decimal there. Currently, it needs to be moved over another 2 places, so that instead of 524, it is 5.24. Hopefully you know that 524 doesn't fall between 1 and 9.999, but 5.24 does. Which means our 524 times 10 to the third is going to turn into 5.24 times 10 to the 5. We moved it over twice to the left. Our big number got smaller, so we'd increase it another 2 times. Down there at the bottom, 0.0026, same idea. That coefficient does not fit between 1 and 9.99999. If I wanted to make it fit between 1 and 9.99999, I couldn't have 0.0026. I would have to have 2.6. So I'm going to move it another 1, 2, 3 times, which means my 2.6 turns into 10 to the negative 8. It needs to be divided essentially 3 more times by 10. So we got 3 more times more negative. So we increased it negatively. Essentially you're just adding negative 1. Well, negative 5 plus negative 1 is negative 6, plus another negative 1 is negative 7, plus another negative 1 is negative 8. So on your calculators, which you should have some kind of graphing calculator, or at least the ability to do scientific notation. There's some that we have available for you to borrow, but we highly recommend that you get your own, because we can't guarantee that we have enough for everyone, because we don't. So you do need to be able to do scientific notation on your calculator. I'm going to be real honest. Y'all tend to be very bad at typing numbers into your calculator unless you practice. So it's going to seem a little ridiculous that we're making you type this kind of stuff into your calculator, but you really do need to get better at it. General steps, you need to type in your coefficient first. Then you're going to hit a button that's generally in the upper left-hand corner of your calculator that says second. What that button does is basically give every button on your calculator a new function. So when you hit second, and then you go and press the comma, it's not going to put a comma. What it's going to put is a little e symbol. That symbol to your calculator reads as times 10 to the power of whatever number you type next. So if I wanted to type 1.57 times 10 to the 23rd in my calculator, you'd type in 1.57, your coefficient. You'd hit second comma, which is going to put this little E button. That's what you'd see after step 3. Then you're going to go ahead and type in your exponent, 23. In your calculator, that's how that is read. Then you just hit enter. You need to be able to understand that this number at the bottom, this number right here, means the same thing as this. When you put your answers on exams, a lot of the time your calculator will spit out this bottom number. You cannot write this E as an answer on your exam. We will not accept it. We'll take a point off, or 2. I don't know. Depends on how we feel. If you want to get all 100% of the time credit, when your calculator spits out that 1.57 E23 or whatever the scientific notation number is, you need to transcribe that into actual scientific notation. This is some examples of the calculations that you're going to have to be able to do. I highly, highly, highly recommend that you get your calculator out right now and you start practicing typing in these numbers into your calculator. Okay? Typically speaking, if you're using the E function, like we just looked at the last slide, you don't have to worry about parentheses. The E function will always ensure that that coefficient goes only with that exponent. If you want to type in the times 10 to, hit the little caret, type in an exponent, you can do that. You're totally allowed to. But if you do, you need to ensure that every number you type in has parentheses around it every single time. That is the only way to ensure that the calculator doesn't mess up and combine the different exponents, combine the different numbers in an incorrect order. Your calculator is a machine. It doesn't think. You tell it what to think. So please, please, please spend some time practicing typing these calculations into the number, typing these numbers into your calculator. These are the answers that you should be getting when you type in these numbers into the calculator. If you're not getting these numbers, you are typing it into your calculator wrong. It is that simple. Now, on a test, we would take either one of those answers. Both of those are technically correct, unless we specify how we want your answer. So read the directions very carefully. We would not accept 4.08 times 10 to the 17 like that. You would have to translate that into that. You got to be able to read that E as times 10 to whatever power comes next. However, we will take either standard or scientific notation, assuming the directions don't specify otherwise. Even if you are using that E function, there will still be times when you need to use parentheses. Using the E allows you to cut down on parentheses, though. So for number 4, for example, if you're using E, you only actually have to have parentheses on the bottom. If you don't, let's say, for example, you do type exactly like this without your calculator, or without parentheses into your calculator is going to spit out this answer right here. The thing is, that answer is wrong. That's not what we're looking for. Order of operations says you need to do everything on top together first, everything on bottom together first, then next, then you can divide the top number by the bottom number. So when you do this in your calculator, everything on the bottom needs to be together in a set of parentheses. If you're actually typing it in like this, times 10 to the whatever power, you might need some extra parentheses. But if you're using the E function, you'll only need that one set around everything at the bottom. This is what is considered the correct answer. Please make sure, type this into your calculator, make sure you can get to that answer. If you're struggling or if you're having trouble or you can't figure out why your calculator isn't spitting out the right answers that we're telling you what should be the right answers, please come see us. Let us show you how to type this into your calculator, because otherwise you're going to get it wrong on the learning checks, you're going to get it wrong on the homework, and you're going to get it wrong on the tests. So come see us, let us show you how to type it in so that we are good to go. Practice typing this stuff in. You will mess this up if you don't practice. It's just kind of a fact is y'all don't know how to use the calculator very well yet because you haven't had to. So now it's time to learn.